Hello, my name is Muhammad Hakim bin Rajabali and I am the presenter of this type. So today I will present to you guys about our current project for the KIG 2012 Mechatronics 1 Household Electrical Simulation using MATLAB and Simulink. Let's go. So for this project, the problem statement is a circuit design of household device connected to the renewable energy source. For example, solar energy is to be met and analyzed using Simulink or MATLAB. The objective for this project is to design an electrical circuit connecting source to the chosen device using MATLAB and Simulink. Second, to calculate the total impedance current in each branch of the circuit, total current voltage in each the branch of the circuit, and total voltage and total power required in the circuit by manual calculation and Simulink MATLAB simulation. Third, we need to calculate the voltage, the current, and the torque in the equivalent circuit by motor and by manual calculation. Also fourth, to draw motor torque current characteristic. The method we use for the projects is circuit modeling. Selected household device are television, lamp, fridge, oven, and washing machine. They are represented as resistor, capacitor, and inductor components, except the motor. Also, when we go deeply into the device, we can also know there are components in the device which is related to our project. As we can see here, the TV, they have the RC equivalent circuit, which is in one circuit, they have resistor and also the capacitor. In the lamp, they have RL equivalent circuit, which is in one circuit, they have resistor, and also the inductor. In the fridge, they have RLC equivalent circuit, which is in one circuit, they have resistor, inductor, and also capacitor. Three of them in one circuit. Also, we can see oven and also washing machine. Oven stand for the pure resistive circuit, and washing machine induction single phase. Second thing that we can do is circuit construction. All appliance subsystems were connected in parallel to a single phase AC voltage source operating at 15 Hz using Simulink Simscape electrical with appropriate electrical reference. The third thing that we need to do is the transformer. A 2-1 idle step down transformer was connected to the induction motor branch to supply the motor at 115 volt RMS, while the remaining branch operated at 2 to 9.9 V RMS. Next, what we need to do is we need to do an electrical measurement using sensor block in Simulink. Also, plot the torque current graph for motor. Also, manual calculation for the appliance and also motor validation. For the last one, which is the power source, the household electrical system is assumed to be powered by a solar system energy source. Solar photovoltaic PV system generate DC electricity which is converted to an AC using the inverter. The inverter regulates the output voltage and frequency to standard household value, single phase 15 Hz. For simulation, the solar system is modeled as an ideal single-phase AC voltage source. Nominal RMS voltage is assumed to be 2 to 9.9 voltage as 15 Hz. Also, the internal PV panel and inverter control dynamics are not considered in this study.
Now I will explain the simulation setup. Starting with the source parameters, the AC voltage source is defined with a peak voltage of 325.27 volts, which corresponds to 230 VRMS, and a frequency of 50 Hz, representing standard household supply. The television is modeled using an RC equivalent circuit representing resistive and capacitive behavior of an electronic components. The values used are 441 ohms for resistance and 3.5 microfarads for capacitance. So next, this slide shows the Simulink implementation of the TVRC equivalent circuit used in this simulation. The lamp is represented by an RL circuit because lighting loads can have inductive characteristics. The resistance used is 882 ohms and the inductance is 10 microhenry. This slide shows the Simulink model of the lamp's RL equivalent circuit. The refrigerator is modeled as an RLC circuit since it contains a compressor motor and electronic components. The values used are 119 ohms, 0.334 Henry, and 3 microfarads. This shows the Simulink implementation of the refrigerator's RLC equivalent circuit. The oven is modeled as a pure resistive load, since heating elements mainly convert electrical energy into heat. The resistance value used is 35.3 ohms. This slide shows the resistive subsystem of the oven as implemented in Simulink. The washing machine is represented using a single-phase induction motor model. Unlike other appliances, this model includes both electrical and mechanical dynamics, such as rotor speed and electromagnetic torque. This slide shows the internal configuration of the induction motor block in Simulink, where electrical input is converted into mechanical output. Here we can observe another part of the motor simulation setup, focusing on measurement and signal outputs. This slide begins the simulation results section, where we analyze voltage, current, and power behavior of the system. This slide shows the total instantaneous power of the household system, which varies sinusoidally due to AC supply and reactive components in the circuit. This result shows the electrical response of one of the appliance branches during simulation. And this slide presents another measured waveform used for performance analysis. And next, here we observe additional system behavior under the same supply conditions. This diagram further supports the analysis of voltage and current characteristics in the circuit. This result helps verify that each appliance operates within expected electrical limits. This graph shows the torque current characteristics of the single-phase induction motor used to represent the washing machine. From the graph, we can see that as current increases, the motor torque also increases. At the starting condition, the motor draws a high current which produces a high starting torque needed to overcome inertia and begin rotation. As the motor reaches its normal operating speed, the current reduces and the torque stabilizes to match the mechanical load. This relationship is important because it shows how electrical input directly affects mechanical output. The curve also helps validate that the motor model in Simulink behave according to induction motor theory, where torque is strongly dependent on stator current, especially during startup and load changes.
Next, we go to the manual calculation parts. From the source, we have Vs to be 229.9 V RMS at 50 Hz. Since the loads are connected in parallel, the RMS voltage across each non-motor branch is equal to the source RMS voltage, which is 229.9 V RMS. Next, we account for the TVRC equivalent subsystem. Given the resistance to be 441 ohm, the capacitance in parallel to be 3.5 microfarad, the capacitive reactance can be calculated using the formula 1 over omega CTV, where omega equal 2 pi f is equal 1 over 314.16 times 3.5 times 10 power of negative 6 give us 909.46 ohm. And next, we calculate the resistor current in phase, which is Vs divided by RTV, and we have 0.5213 ampere. And this aligns with our simulation results. Next, we calculate the capacitor current magnitude by dividing Vs with XCTV, and we get 0.2528 ampere, and this also aligns with our simulations result. And the total TV branch for the current phasor is calculated to be 0.5213 plus J 0.2528 ampere. For lamp RL equivalent subsystem, given the resistance to be 882 ohm and the inductance to be 10 millihenry, then we calculate the inductive reactance using the formula omega L, which gives us 3.1416 ohm. Next, we calculate the impedance magnitude, which is R squared plus XL squared square root, and we get 882.01 ohm. And then we calculate the phase angle, and we get 0.204 degree. The current therefore lags the voltage by this angle. We can then write the I lamp in phasor form and also the magnitude, which is 0.2606 ampere. Next, for the Frisch RLC equivalent system, given RF equal 119, LF equal to 0.334 Henry, and CF equal 3 microfarad, we then calculate the inductive reactance using the formula omega LF, and we get 104.93. Then we can calculate the phase angle of RL path, and we obtain 41.8 degree. Then we can calculate the series RL impedance magnitude using the formula square root RF square plus XL Frisch square, and we obtain 158.63 ohm. And then we can calculate the RL path current magnitude, and we obtain 1.449 ampere. We also can put it in phasor form. Next, we calculate the capacitive reactance using the formula 1 over omega CF, and we obtain 1061.03 ohm. And then we can calculate the capacitor current magnitude, and we obtain 0.2166 ampere, and we can also put it in phasor form. For oven R subsystem, we have R oven equal 35.3 ohm. So we can calculate the I oven, which is equal V source divided by R oven, and we obtain 6.514 ampere, and we can put it in phasor form. Because the motor is supplied through a transformer, its contribution to the source side current must be referred to the 230 voltage side using complex power. Using the formula shown, we get the magnitude for the current that contributed by the motor equal 2.89 ampere, or 1.772 minus J2.289 in complex form. The total source current is obtained by summing all branch current phasors. That is, I total equal I TV branch plus I lamp branch plus I fridge branch plus I oven branch and plus I motor branch. This phasor summation is implemented using MATLAB to avoid algebraic error, and the resulting magnitude is 10.53 ampere, which is the same as the simulation results. The equivalent impedance seen by the source is therefore V source divided by I source, and is equal to 21.9 ohm. Next, we can calculate the total apparent power drawn from the source using the formula Vs times Is, and we obtain 2.42 kVA. As we know, the motor is connected to other branches and to the power source in parallel connections. For simplicity, we don't calculate the parameters for the motors using the equivalent circuit of the single-phase induction machine. In the simulated model, the washing machine motor is subjected to a step mechanical load using an ideal torque source, which gives us the load at steady state is 2 Newton meter. Using the ideal rotational motion sensor, the steady-state angular speed of the motor at the 2 Nm load condition is measured from simulation as 50.2513 radian per second. The fundamental relationship between mechanical power, torque, and angular speed is given by P equal tau omega. From the simulation, the real electrical input power to the motor at 2 Nm is 407.4596 watts. Substituting the measured values, we have torque to be 8.11 Newton meter. Next, for the motor voltage, the motor terminal voltage is determined by the transformer turns ratio with transformer ratio of 2 to 1. The secondary motor side voltage is calculated, and we have 115 volt RMS. The motor RMS current is obtained from the simulation using current sensor placed in series with the motor branch on the secondary side of the transformer, and at steady-state operation with load torque of 2 Nm, which gives us the I motor to be 5.787 ampere.